Hey there, chemists. Welcome to one of my favorite lessons in the nuclear chemistry unit, which is all about half-life and how we can use radioisotopes for useful applications. So let's go ahead and take a look at a quick video to get us started.
Archaeologists announced they had unearthed the oldest Homo sapien remains ever discovered. Analysis reveals the fossils date back about 315,000 years, making them more than 100,000 years older than those previously thought to be the oldest. The history-altering fossils were found on a hillside in the Moroccan desert. Researchers recovered skull fragments, teeth, and other bones from 5 individuals, along with stone tools and evidence of fire usage. The discovery reveals that the bone structure of these early humans' faces are not much different from ours.
To me, it's quite striking is that the reason why we connect these people to us is their face, the way they look. So it's people we would recognize like us if we would cross them in the street.
The fossils also change the way we think about where early humans developed. They were discovered on the western edge of the African continent, thousands of miles away from the so-called Cradle of Humanity in Ethiopia, the site where the former oldest human remains were unearthed, challenging another fundamental idea, that our species evolved in just one location.
You know, it's so fascinating.
All right, and we're going to go ahead and pause it right there. What I think is so cool is that using these radioisotopes, more specifically carbon-14, which we'll talk about in just a moment, we can use these radioisotopes to help us determine how old different components or different fossils are that we find, right? I'm sure you guys have already learned about this a little bit, but now we're going to talk about it more in terms of the chemistry and what is called half-life. So what we're really going to look at is how we're able to determine the age of the fossil. All right, so taking a look here, I have 3 different nucleus or nuclei of carbon, carbon-12, carbon-13, and carbon-14. Below them, you can see the number of protons and neutrons in each of these, and you can see actually at what percentage that of the 100% of carbon on this Earth that we can find these different amounts, carbon-12 being the most prominent. So most of our naturally occurring isotopes of carbon are considered stable. And why is that the case? Based on what we learned from yesterday or in our previous lesson, remember that the stability of an atom is determined by that proton to neutron ratio. And the closer that ratio is to 1:1, the more stable our atoms are. So carbon-12 is most stable because it has a 1:1 proton and neutron ratio. Which of our carbon isotopes, carbon-12, 13, or 14, is most unstable? Again, this depends on the proton to neutron ratio. The greater the difference, the less stable it is. So we have 6 to 8. This is going to be our least stable. So carbon-14 is least stable. Now, carbon-14 is the radioisotope that's used to help us do carbon dating or to help us determine how old a fossil may be. And again, we'll talk more about the other radioisotopes later in this unit, but let's talk a little bit more about carbon dating and the radioactive decay it undergoes. So based on reference table N, I want to go ahead and take a look at the the type of decay that carbon-14 undergoes. So looking here on reference table N, I see that carbon-14 undergoes beta decay. So let's go ahead and write out that beta decay reaction. We start with 14 and carbon is 6, okay? And it's going to undergo beta decay 0 minus 1e. And we need to determine the missing product here. Now, again, when we're doing that, what we like to do is just use the mass here, 14, and we have 0 mass here, which means our missing nuclide has a mass of 14 as well. From there, we have an atomic number of 6. Beta decay is a -1, which actually means that our nuclide is going to have an atomic number of 7 to balance out that -1. And so the missing nuclide is going to be not carbon, but in fact, we need to use our periodic table to figure out that it is nitrogen. So archaeologists often use those radioisotopes, and again, like I said, specifically carbon-14 to date fossils based on what's called the half-life. And so let's go ahead and take a moment and just define half-life. Half-life is the amount of time it takes 1/2 of a sample to decay. Okay, and the half-life never changes. The rate never changes. It's always the same. Rate doesn't change. Okay, and so what is our half-life? Where can I find this information? We can actually find our half-life information on reference table N. And so right next to that decay mode type, we can also find the half-life. So according to reference table N, what is our half-life of carbon-14? So again, we're going to go ahead here and glance at carbon-14, and we're going to notice that there is a whole column here called half-life, and carbon-14 has a half-life of 5,715 years. 5,715 years, which means that it takes almost 5,700, a little over 5,700 years for half of a sample of carbon-14 to decay. And so let's say I have an original sample of carbon-14 that was 50 grams. How many grams would remain after 5,715 years? Now, the easiest way that I like to complete these problems, or what I find is easiest with these, is again, first to determine the half-life, okay? So we're gonna figure out how many half-lives this has undergone. So carbon-14 has a half-life of 5,715 years, and therefore this has undergone 1 half-life, okay, during that time span. Now, what I like to do with these problems is to write out my starting amount. So I'm starting with 50 grams, and I'm going to use arrows to represent half-lives. So to do this, I'm going to say, okay, I have to go 1 half-life. I need 1 arrow. And in that time, my sample is going to decay to exactly half the original amount. And so my amount is 25 grams. Okay. And again, just make note that this 1 arrow, or this arrow, represents a half-life. Okay. And the arrows may seem kind of silly for this problem, but they're going to come in handy later for some of these more challenging half-life problems. All right, so what about 28,575 years? Again, this is carbon-14, so it has a half-life of 5,715 years. And so how many half-lives will it undergo during that time? It's going to undergo 5 half-lives. Okay, half-lives. I don't know, however you want to call it. I'm not using the correct grammar there. So half-lives. And so that means that in my problem, I'm going to need to do a total of 5 arrows. So my starting amount was 50 grams. Okay, so 50, 1 arrow, 25, 2 arrows, 12.5, 3 arrows, 6.25, 4 arrows, 3.125, and that's again 1, 2, 3, 4, and now our 5th arrow is 1.625 grams. Okay, and this is why I like this arrow method. It helps me keep track of the number of half-lives I've used, 1, 2, 3, 4, 5, to match it to my initial problem. All right, let's say that we had something different. This is helping us figure out how many grams there are remaining. What if instead I wanted to figure out how much time has elapsed, kind of like how the archaeologists determine the amount of time elapsed? So suppose my initial sample of carbon-14 was 28 grams, and now I have only 3.5 grams remaining. How much time has elapsed? So in order to complete this problem, we're going to go ahead and start with our secondary step from above with our initial mass, 28 grams, okay? After 1 half-life, I would have 14 grams. After 2 half-lives, I would have 7 grams. And after 3 half-lives, I would have 3.5 grams. And so that's what it was asking. When will I have 3.5 grams? How much time has elapsed? Well, we've undergone 1, 2, 3 half-lives. Each half-life is 5,715 years. And therefore, that means that 17,145 years have elapsed. One last problem for you. Okay, what fraction of a carbon-14 sample would remain after 32,290 years? So we're going to go ahead and we're going to take that time, 34,290, and divide that by the half-life time of 5,715 years. This tells me that we've undergone 6 half-lives, or half-lives, I don't know, whichever it is, okay, and we need to figure out what fraction remains. Now, in this problem, note that whenever you're working with fractions, at the very start, your initial fraction is always going to be 1, right? So your initial fraction is 1, and we need to go 6 half-lives. So after 1, we'd have 1/2 of our sample. After 2, we'd have 1/4 of our sample. After 3, I'd have 1/8. After 4, I would have 1/16. After 5, 1/32. And then after 6, I would have 1/64 of my initial sample. All right, everybody, we're going to do more practice with this in class tomorrow and maybe some different types as well. Thanks so much for watching, and I'll see you guys tomorrow.